Good afternoon, everybody. Welcome to cloudy afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Hi, everybody. Now, before I forget, I would like to wish everybody who's celebrating Passover tonight a happy Passover. And for those of you who have been and are celebrating Ramadan, a happy Ramadan. And for those of you who are celebrating Easter this Sunday, happy Easter. If you're not celebrating any of those three I just mentioned, I hope you have a happy weekend. I think I covered all my bases. All right, let's get going. Let me move this over. I like to remind everybody a week from today, I will be giving test number 3 online. And you'll be downloading, just like you did test 1 and 2, a PDF file that's password protected from D2L once I put it in there. And I'll send on Wednesday at the end of class and lab, 4 p.m. earlier, most likely a little earlier, I will send out an email with the password for test number 3. And you'll have from Wednesday until Thursday, 1 p.m. to finish test number 3 and upload your test answers as a single PDF file to the D2L area, the assignment area D2L. It should take about 40 minutes or so for you to actually finish the test if we were face-to-face. But since I'm not timing and we don't have to get the lab because we're online, take as much time as you need. Take as much time as you need. I started doing that on the internet when I had one student say, oh, downloading everything, I didn't have enough time to finish. And I said, you should have taken extra time. Now I give extra time. Test number 3 has 9 pages, 10 problems. Some of the problems are multiple part. I have never and will never give a multiple choice question in Chem 170. Don't. It will cover carboxylic acids, esters, carboxylate anions, amines, amine salts, quaternary ammonium salts, and amides and heterocyclic compounds. Now, the point breakdown, 7 points general knowledge, nomenclature 38, reactions 60. It adds up to 105. And that means there's five bonus points. You pick out which are the bonus points. I don't do that. As with all my notes tests, it's not open note test. And the Monday afterward, or that, I'm getting ahead of myself. Next Monday, I will do my world famous review for the next test number 3. And on Wednesday, the day I do give the test, we'll still have our regular Zoom meeting. Now, I sent this out while you were beginning a spring break, so hopefully you did have a good spring break. And let me remind you, nomenclature questions are, here's the compound, give the IUPAC or common name, because with amines, I didn't ask you to learn IUPAC names. And it will be, here's the name, draw the structure. Reactions, give the organic product or products are the following, or I'll have a couple of them, I forgot how many, 3 or 4, maybe even 5, maybe 3 or 4. Give the starting material for the following reaction or materials. And before we go on, I've got to ask, did anybody happen to think about esters when you were smelling flowers or fruits or vegetables? Did you happen to look at a bottle? This is not it, but pretend it's a bottle of vinegar and it contains acetic acid. which is a carboxylic acid. Did you do that? If you were going to buy some nail polish remover, did you look at the bottle to see if it has ethyl acetate, which is nail polish remover, which is an ester? Remember, organic chemistry is all around you. I stole that from SpongeBob, and it won't hurt you to think about it outside of my lecture or lab. All right, I promised I'd go through the amine, amide, and everything else problem set, so I better do that. Now, when I wrote this problem set, I got carried away a little. There are a few things I crossed off that I'll never put on a test. All right. Give the IUPAC, and notice now it's different, or common name for the following. And how do you do that? You look for the functional group. How do you look for a functional group? You look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like that. And if we look at A, we have a nitrogen, and it's got an R group on it. This is an amine. And the common name, name the R group as the alkyl group it is. And since amine, add the word amine. And this would be, I made a mistake. That should be N-butylamine. Again, that should be N-butylamine. Now, if we look at B, we have a nitrogen, isopropyl, ethyl, and it doesn't matter which goes first. You could have put isopropyl first, ethyl isopropylamine. Now, benzene ring with NH2, the common name became the IUPAC name, that's aniline. Cross off D, I shouldn't have put it down. Here we have a quaternary ammonium salt. We have 4 different groups on a nitrogen with a plus charge, a halogen anion. And you name each group as the alkyl group it is, dimethyl, diethyl. Then for quaternary ammonium salts, you add the word ammonium halide. And for X minus, when X is chlorine, Cl minus is called the chloride anion. When X is bromine, Br minus is the bromide anion. And when X is I minus is iodide. Now there are a lot of other let me say that again. There are a lot of other anions besides the halogen anions, but I'm not going to cover that in this class. Made it a little easier for you. All right, now if we look at G, what do we have? We have a nitrogen. It's got 3 hydrogens with a plus charge in an alkyl group and a halogen anion. This is an amine salt. And you name amine salts the same way as you name quaternary ammonium salts. The only difference is you never have 4 alkyl groups. With a quaternary ammonium salt, you always have 4 alkyl groups. And therefore, that's N-propyl. That's the only alkyl group. And then you add like a quaternary ammonium salt, ammonium halide, in this case is chloride. Now, let me just remind you, because something I worked in very heavily for a number of years in the chemical industry, quaternary ammonium salts, what's one of their main uses? As a fabric softener. What's another one? Antimicrobial, antibacterial compounds. And if you notice, remember the mouthwash I brought, the scope equivalent from Walmart, that has a quaternary ammonium salt, keeps my gums nice and healthy. If it wasn't, I'd be screaming out, I'd be in pain, and I'm not. Nope, I'm not. No, I'm not in pain. But remember, quaternary ammonium salts can be used in mouthwash. And if you know those antibacterial towels like you get at any store, most stores, they have shopping carts for you to wipe it off. That has a quaternary ammonium salt. I don't know if I told you this. Time out for a important thing for your daily life. I think I might have, but I should tell it again. A number of years ago, I saw 2 reports where someone went to stores with shopping carts and they wiped down the handle and the whole area around the shopping cart that you would touch. And they found, I think it was like about 85, 90% of them had fecal matter on them. Yep, fecal matter. Well, if you think about it, those seats you put the baby in, think about that. No, don't. And once I read that, and they started putting those towelettes, antimicrobial, antibacterial towelettes, which have quaternary ammonium salt in them, I use those religiously. As soon as I get the cart, I go over to where they have the dispenser, grab 2 of them, because the first one's usually dry, and I'll wipe down the cart, the seat area and everything around the cart, anywhere where a baby might have been sitting or touching, and then I do and wipe my hands off. And I'm not germ-free, yuck clean, if there was yuck there, fecal matter. Ugh, but it's true. Now that I grossed you out for today, we can get back to organic chemistry. The other type of nomenclature question is, draw the condensed structure for the following molecule. How do you do this? You start from the right and move left. Ethylamine, well, ethyl group. Remember, amines, the nitrogen has 3 bonds to it. Amines, the nitrogen has 3 bonds. If it doesn't, the remainder are hydrogens. Again, in amines, nitrogen has 3 bonds. And if it doesn't have 3 bonds, then you use hydrogens, like carbon has 4 bonds. Now, if we look at B, an amine, and there's a tert-butyl and an ethyl group, and it doesn't matter which side you put. Now, molecule C, cross off. I shouldn't have put that on there. Sorry. Now, D, that's a molecule near and dear to my heart. That'll make me a lot of money, pay for my house, my cars, got me around the world. When I worked for chemical companies that made quaternary ammonium salts. And you see ammonium chloride, that can be either a quaternary ammonium salt or a amine salt. But if you see dimethyl, 2 methyl groups, and ditallow, and I taught you, and we'll learn more about it when we get into fats and oils, you abbreviate a ditallow by R sub T. So I have ditallow, dimethyl ammonium chloride. Now, there's another way that you could write it that would be perfectly acceptable on a test. Instead of the shorthand, remember, organic chemists are lazy. I am when it comes to certain things. This is another way. 2 sides have an R sub T, 2 sides have methyl, and you have the anion. Now, you do not have to write charges, but I always do. Good habits, Dr. White never changes. And E, omit also. All right, let's look at some reactions. Draw the structure for the organic product or products for the following reaction. And what do we have? Ammonia. And if we look at the second one, CH3I, a halogen on a carbon, RX. X I don't have written there, but that could be chlorine, bromine, or iodine. In the presence of base, you make a primary amine. The carbon with the halogen is the carbon the nitrogen is bonded to. If you look at the methylamine of A, it has 2 hydrogens. Why? 3 bonds to nitrogen. All right, if we look at B, primary amine, halogen on a carbon alkyl halide base, you make a secondary amine. The carbon with the halogen is the carbon the nitrogen is bonded to, in this case, the center one. And my R group was methyl, R prime isopropyl, and I make methyl isopropylamine or isopropyl methylamine. And you could have the sides flip, the isopropyl first, the methyl second, and there are other ways of writing it. Ooh, C. That's a reaction I know better than most people on this planet. Yes, I'm an expert in quaternary ammonium salts. And this is a reaction we did when I was at AXO to make the dimethyl dital ammonium chloride, which is used mainly for a fabric softener. And you start with ditallomethylamine, a tertiary amine. I don't have it written here, but R prime and R double prime in this reaction are alkyl. And you start with a tertiary amine, alkyl halide, and base, you make a quaternary ammonium salt. In this case, my favorite, dimethyl ammonium chloride. D, we have an amine plus what's HCl, HX, and acid. Amines are bases, you get a proton transfer, and you get a salt. Now, the way I had it written here when I did this, wow, back in 2013, wow, that's a while ago. Oy vey, hopefully you all know what oy vey. That's a decade ago. I've been doing this for a while. But a better way to remember that reaction. Which I did when I taught you this semester. This is straight acid base. Amines are bases, R prime and R double prime, one, both, or none can be hydrogen. And you make an amine salt. You don't have to draw the charges, but I do. If you want to, you can too. I have a number of them. On G, cross that off. But it's time for me to tell you something that reminds you that you probably don't know. If you look at a lot of personal care products, mainly cosmetics, that molecule in G is diethanolamine. That's the common name. And it's a base. And it's used to adjust the pH in cosmetics. So if you put something on your face, cosmetics, your skin doesn't get affected if the pH was too low. That's used to adjust pH. All right, let's look at H. Here we have a carbon nitrogen triple bond. It has 2 pi bonds, 1 sigma bond. And guess what? You had hydrogen excess and a catalyst. Catalyst can be nickel, platinum, or palladium. You break the 2 pi bonds. And each atom of the triple bond gets not 1, but 2 hydrogens. And R, in this case, is ethyl. And this carbon gets 2 hydrogens. You can write it this way or this way. And this nitrogen gets 2 hydrogens. You can write it like this or NH2. And as I mentioned, that was the first project. I worked with a nitrile with 5 carbons called pentyl nitrile. And I give you a few more examples to have fun in. If you look at J, what have I done? The organic chemistry's favorite trick on a test, put a big, scary molecule. And if you don't know what it is, that's a big, scary molecule. You go, eek. Hopefully you don't go eek ever on my test. But this is an R group that comes along. Nitrile, carbon, nitrogen, triple bond. The only thing that changes is you break the 2 pi bonds, and each atom of the triple bond gets 2 hydrogen. All right, let's move on. If we look at L, and same as K, and same as M, we have, what's different? Carboxylic acid. What's different here? Amine. Now, I don't have here, but R prime and R double prime, one or both, or none, can be hydrogen. And what do you form? An amide. Now, if you notice, I also have water, but the question asks, give the organic product a product, so you don't have to put that down. If you want, go right ahead. And what's R methyl? What's R prime? Methyl. And here we have the amide. Carbonyl, methyl group on there. Nitrogen, R prime was methyl, R double prime was hydrogen. Doesn't matter which you have, which on nitrogen. Now, listen carefully. In an amide, R prime and R double prime can be hydrogen. An important thing about nitrogen and amide, the nitrogen atom in an amide has 3 bonds to it. So amines and amides, the nitrogen has 3 bonds. Three. I'm burning it into your brain. 3. In quaternary ammonium salts and amine salts, the nitrogen has 4 bonds to it. 4. I gotta get that finger fixed one day. 4 bonds to it. Now, if you look at L, R prime and R double prime are hydrogen, and you make this amide. If you notice, I give some more examples here. It's R prime and R double prime are methyl. Remember, I forgot to say this in a long time. Do you break carbon-carbon single bonds? No. I'll say that again in slow motion. Do you break carbon-carbon single bonds? No. That was slow motion. Seriously, remember, 4 bonds to carbon, you don't break carbon-carbon single bonds, and nitrogen in amines and amides, 3 bonds, nitrogen in quaternary ammonium salts and amine salts, 4 bonds. And here, what's are these 2, 4, 5 carbons still attached to the carbonyl? Nitrogen making amide. What's R and R prime in this reaction? Methyl, so you get this amide with 2 methyl groups on nitrogen. And remember, the carbon with the NH nitrogen in the amide or in the amine, let me back up more. That's like when you rewind a tape deck. Any of you ever used a tape deck? Probably not. Oh, my generation gap is showing. All right. The carbon in the amine used to react with the carboxylic acid to make the amide is the carbon on the nitrogen that is bonded to that carbon. Notice the NH2 is on the center carbon. The nitrogen carbon, the atom, is on the center carbon of that R prime. All right, now, Once you have an amide, what can you do with it? React it with acid and water. And I'll be using the acid HCl. You could use other acids, but what's the reason for using HCl? It's the acid in your stomach. And we'll talk later how that acid breaks down certain foods, carbohydrates, fats and oils, and proteins, so your body can use them to do whatever your body does with them. Remember, last time I had biology was freshman year high school. Not that there's anything wrong with biology, but by then I already knew I was going to be a chemist. Yep, by my freshman year. I think even by 8th grade, even earlier, my father loved chemistry. He was a pharmacist, but he loved chemistry. I wonder why I became a chemist. Don't know. And if you take an amide, excuse me, I'm getting all choked up over this good stuff. You take an amide, react with HCl and water, acid hydrolysis of an amide, you get back the carboxylic acid you would have used to make that amide, plus not the amine you would have used to make that amide, or in this case, ammonia, because ammonia and amines are basic. They react with acid immediately to form the amine salt. In this case, R is methyl, so you get acetic acid. R prime and R double prime are hydrogen, and you get ammonium chloride, which technically you don't have to write down, which is why I'll never put this type O question where it's NH2, because that's inorganic. But I will do like in P, and remember R prime and R double prime, one can, or both or none can be hydrogen. And here R is a benzene ring, so you get benzoic acid. R prime is methyl, R double prime is hydrogen. You add 2 more hydrogens to the one on there, that's why you get 3. And you can write this like this, or you can do it the way I have in bracket. Either one, I will mark correct. But if you put down the amine, I'll mark it wrong. You're wrong, out of there. And I have a few more examples. Now R, we have this. Let's do S. We have this amide. How do you know? Carbonyl, nitrogen, R group on the carbonyl, R prime and R double prime. Now remember, R prime and R double prime can be hydrogen. And you can react with other bases. I'm going to stick to sodium hydroxide and water. And you get the carboxylic acid? No, you get the carboxylate anion of the carboxylic acid, because in the presence of base, the carboxylic acid you get reacts immediately to form that carboxylate anion. But you do get the amine you would have used to make that amide. So if we look at S, R is a benzene ring, R prime methyl, R double prime hydrogen. So you get methylamine and sodium benzoate, this carboxylate anion. And I have another example, which is a little more complex with the same reaction. Oops, everybody, don't look. If you look here for T, I made a mistake. Well, I told you I don't walk on water unless it's frozen. Even then I stay off it. That second N should really be an H. This should be an H. Whoops. Somebody moved the line from here to here. You believe that? I got a bridge in downtown Chicago. I'll sell you. I don't. I made a mistake. All right. Let's look at some synthesis problems. And if we look at A, what are we trying to make? What's different? A nitrogen, 2 R groups. It's a secondary amine. How do you make a secondary amine? You start with a primary amine and alkyl halide. What's R? Well, I could say R is methyl, R prime is ethyl. And since I don't show you anything, you could use any halogen, bromine, chlorine, or iodine. And here I have methylamine, R prime is ethyl, so you get ethyl bromide. But I could have said ethyl is R and methyl is R prime. And then I would have gotten this second one, ethylamine. And here the R group for the halogen, alkyl halide, is methyl. And I just picked methyl iodide or iodide. You could have used chloride or bromide too. Now, if we look at B, well, I've got a lot of them here. What are we making? A quaternary ammonium salt. And, oh, I made another. Oh, I'm going home. I am home. That should be a plus on the nitrogen and X minus. Well, I got sloppy in my old age. Anyways, how do you make a quaternary ammonium salt? Tertiary amine alkyl halide. I even forgot the arrow in the base there. And if I call two of these methyls R and R prime, and the ethyl R double prime, and the R triple prime ethyl, I would get this top reaction. If I did it the other way around, this would be the other. Either one are correct. All right, let's move on. Here we have what type of molecule are we making? A primary amine. We're reacting with hydrogen excess and a nickel catalyst. Remember, a catalyst can be nickel, platinum, or palladium. And what do you start with? A nitrile. What's R? Two carbons ethyl, my carbon nitrogen triple bond. Now, when you're doing this reaction, any of them, always remember there's 4 bonds to carbon, 3 bonds to amines, 3 bonds to nitrogen amide, and 4 bonds to quaternary ammonium salt nitrogen and amine salt nitrogen. And the more important thing, or maybe not more, but very important, do you break carbon-carbon single bonds? No. So if we look at C, I start with 3 carbons. I better end up with 3 carbons and a nitrogen, and I do. Now, if we look at D, what do we have? What do you react with acid and water to make a carboxylic acid and an amine salt? And the answer is an amide. R is ethyl. One of these R groups is N-propyl. The other is a hydrogen. And therefore, I have my carbonyl. R is ethyl. R prime, I can call hydrogen or N-propyl, doesn't matter which you have which here. And then the other one is N-propyl. And finally, what do you react with base and water to form a carboxylate anion and an amine? And the answer is an amide. And I put the base here instead of over the arrow. You can do either one, and I do. And what's our ethyl? What's our prime? Ethyl. What's our double prime? Hydrogen. And here's the molecule. You could have the hydrogen coming down. And with that, that's a long problem set. Well, there's a lot we covered. And as I mentioned when we finish this chapter, there'll be no more general reactions. We're going to take it out into the real world. So any questions on amines, amides, or anything else like that? But the only thing I haven't figured out yet, so don't ask me what's the meaning of life. All right. Ooh, I got some time. There's something I didn't mention when we were going over quaternary ammonium salts. I'll be finished soon. Well, if we look at this is a tertiary amine. And, oh, excuse me, this is an alkyl halide. This is our triple prime. And you can call this our double prime. And these, because there are two of them, are R and R prime. And what you get is a quaternary ammonium salt. I've been good. I haven't used the slang. I haven't called it QUAT. Oof. But if you're an expert like me and work in this industry, that's what we call them, quats. Oops. I've got R prime on the brain. I did it again. All right. You take this methyl ditalloamine, react with methyl chloride in the presence of base, you make ditallo dimethylamine. Now, when I was working at AXO, our main customer was Procter & Gamble, which we call and everybody else calls P&G. And we had about, this is not confidential because this is a long time ago, about 60 to 70 million dollars a year business just selling that molecule to Procter & Gamble. That's big time money. I mean, big. And Procter & Gamble decided to change the formulation of Downy. And what they did, nope, it's Bounce, a Bounce. And let me look it up. I've got a brain freeze. Wow, look at all the products they have. Yeah, I've got the right one. All right, so Procter & Gamble changed the formulation. What they really changed was the perfume in there. They gave it its scent. They decided to do something else. All of a sudden, the VP of marketing and sales calls me up because I'm responsible for research and development and any kind of problems with dimethyl ammonium chloride for all North America. And I also helped out with Europe and South America too. So he called and said, P&G changed their formulation, and our competitor also sold. If you're in business, you never want to get one key product or from only one vendor. You make sure you have at least two, so if something happens to one vendor or supplier, you can still get it from someone else. And we had the majority of the business, but our competitor, for some reason, and I really got ticked off at the salesman at Procter & Gamble, how come they didn't use ours? And anyways, I'm not going to go into what kind of profanity I know and used that day. But anyways, they used our competitors and they came back. The VP said, now P&G says our quaternary ammonium salt, ditallo dimethyl ammonium chloride, makes the new product stink. What? What's going on? Well, you got to find out why ours stinks. Well, one of the hardest problems in all of chemistry to solve is an odor problem. It is difficult. And this is probably the hardest problem I've ever had to solve. I've done some other hard ones, but this was a doozy. And what made it worse is we're talking millions of dollars of sales, millions of dollars of profit. Well, I started checking and I've got some information from someone that set up a smelling panel, make sure you have no women who are pregnant on the panel, because that sometimes affects the way they smell things. And we couldn't tell a difference. We got a sample of the new and old Downy, and it smelled the same to us. And after during this time, what made it worse is the president of AXO in the United States, when I got to my office at 8 in the morning, I was actually there earlier, 8 in the morning, right around noon and right before I left, 3 times a day, he would call me and he said, "Have you solved it yet?" And I'd have to tell him, no, that was not a fun part of my life. So after about 2 or 3 weeks of me spinning my wheels and everything, I realized there's something wrong. I don't have all the correct information because I don't know how to solve this problem, which is unusual for me. So I called back to our VP of Marketing and Sales and said, I've got to talk directly to who's ever at Procter & Gamble who's saying our product makes the new product stink. And well, it turned out it wasn't that easy. The person in charge of that was a senior perfumer. At that time, I don't know if it's changed now, Procter & Gamble had only 5 senior perfumers, and they were in different parts of the industry or what products they made. There was one for fabric softener and cleaning products. And his job was his nose made sure what the product you bought last year or last month smells like the product you buy today and will smell like the product you buy next week or next month or next year if they haven't changed the formulation. Yes, they have instrumentation that can identify odors, but they're not as sensitive as the human nose. And I found out that this perfumer was guarded and all the others like royalty. And he didn't get to see them. And I talked to my counterpart, who was a research manager who I'd worked with at P&G. He said, I haven't been allowed to ever meet this guy either. That's how guarded these people were. Well, after a few calls, and I talked with the VP of Marketing and Sales, and he went back to Procter & Gamble, they finally allowed me to meet this person. And before I met it, a couple of days before, I got a call from a senior vice president of Procter & Gamble. He said, when you meet this person, I can't remember his name, very nice person. 1, you can't smoke for at least 24 hours if you're a smoker. And I was. Why? You're going to ruin his nose. We don't want that. He doesn't want to be around anybody who's ever smoked, hasn't smoked for a while, because otherwise it affects his nose. The other thing, and he told me point blank, you better be really nice to this person. Don't get him mad, or we're going to cancel all our business with your company. $60 million now. And so I went there. Oh, another quick thing. I said, could my counterpart, Earl Wall, who was the senior R&D manager at Procter & Gamble, could he be in the meeting? I think he should. And the VP said, no. I said, wait a second, he's important. I finally convinced them. Here's somebody in their own company, a senior manager. They wouldn't even let near this person. Finally, I convinced them. Well, we went to the meeting. It was in their research center in Sharonwood. Outside is that, I think it's Cincinnati. I forgot what it is. It's in Ohio. Outside, I think it's Cincinnati, but don't quote me. And here I am in a meeting. There are about 8 people, but it was really between me. I had me and my sales manager with me, VP of Marketing and Sales, and the salesman for that area. We had to work to get them in that meeting. And then a few key people from Procter & Gamble. And it was essentially a meeting between me and him. We sat down, we greeted and everything. And he told me about what he did. And he made a joke. He said, you know something? I smelled a really strong something I was checking, and it just blew out my nose. I should have gone home for today. It stopped working. Nobody laughed, and it was true what he was saying. So I asked him point blank. I said, I have been told our product, our quad, is the trade name is our quad 2HT75, and the name is dimethyl ammonium chloride, makes your new formulation a downy stink. He said, no. I said, really? Well, what's wrong? He said, the intensity of the perfume with your quaternary ammonium salt is less than the intensity of the perfume in the product with your competition. I said, oh, okay. Well, now I know how to solve it, or at least I think I did. After that, we talked and he gave me some advice how to set up, how to smell things. I said, if I send you samples, can you make product and you smell it? Because your nose and you know what you're doing, and I don't when it comes to the level of testing for odor that you're at, and I'll never be at, and nobody in my company is at. He said, all right. So I went, and luckily, and I'm not going to tell you how, we were able to get a sample of our competitor's product. And at that time, there was, I hope he's still alive, this great analytical chemist who was in charge of our analytical department at AXO, Dr. Chunan Wang. Great guy, really smart, sharp analytical chemist. I said, here are two samples. There's something different between the two that's causing the problem. Help me find it. And he was able to identify this one impurity that in our compound, we had, are you listening to this? 200 ppm. In our competitors, they had 100 ppm. And that little difference of a small compound, I can't tell you that because it's still a trade secret. But anyways, and I'm covered by non-disclosure agreements still. But anyways, that small little amount made a difference in what that perfumer smelled, the intensity of perfume in their product. So I figured, all right, I know I've looked at the reaction. I saw how that impurity was made. I changed it so there was 0. We sent him a sample and said, no, it's no good. What's wrong? Says, now yours makes the perfume smell stronger. I said, all right. Well, and I went back to said, all right, if our competitor has 100 ppm impurity, I'm going to get 100. We did it. And luckily, the president of AXO stopped calling me. Thank me for solving the problem. If I look at the time, it's time to take a break. So let's take a 5-minute break. I'm going to go stretch. I hope you enjoyed that story. I'll see you. I'm back. All right, I hope you enjoyed that story. It was about a 8-week period of my life that until I solved it was not fun. No, it wasn't fun at all. It was a miserable time till I solved it. Then I remember when we solved it and everything, I went and with a couple of friends and we partied hard. All right, now, as I mentioned, let me get comfy. I'm comfy now. As I mentioned, if we were face to face each Wednesday, we'd have a 50-minute lecture like I just did, and then we'd go to lab. Now, I've been cheating. I've been using some time on Wednesday to also lecture, which allows you to see more examples. But what that means is we're ahead of schedule. Yay, which is good. So what I'm going to do right now is we're going to have lab, and then you'll get out early. You can all smile now. Or you can frown if you're like Hermione in Harry Potter, who always liked to do schoolwork. Nothing wrong with that. All right, everybody see on your screen the esters lab, and the answer is yes, because they put a new feature in Zoom that they didn't have for years. What screen you see, I would show this and I'd have to ask you, are you seeing this? And sometimes I'd think you did, and Zoom would mess me up and you're not. But anyways, let's look at the carboxylate anion and ester lab. Now, esters are an important part of nature. They're responsible for the odor of fruits, some vegetables I could have put down there, and flowers. They're also used to make polymers, and carboxylate anions are useful. We'll learn later on. Now, this is an ester. This is a carboxylate anion. Now, in this lab, part of it, and this is one of those I wish we were face to face, but there's no way you're ever going to do this at home. It's too dangerous because you'll be working with, if we were face to face, sulfuric acid. Concentrated sulfuric acid will damage your skin. They call it an acid burn because if it gets on your skin, first of all, it feels like somebody slapped hot iron or metal on your hand, skin. I don't know if that's, well, I know it's true from seeing someone else. I have never had an acid burn because I'm really careful around acids and other chemicals too. And that's why I have this caution. Now, what we're going to be doing is the following reaction. Which you already learned, but here H plus is sulfuric acid, H2SO4. And what you make when you react the carboxylic acid with an alcohol, you get an ester. Now, what you would be doing if we were face to face is making a number of esters. Now, the procedure is essentially the same. In a large test tube, you would put in the carboxylic acid, the alcohol, and then carefully some drops of sulfuric acid. Now, to do this reaction, you have to heat it. Now, you don't want it boiling water. Why? Because some of the alcohols would boil off. So what you would be doing, look out, artwork from Dr. White. You can laugh your head off. I'll never be an artist. My mother was a very good amateur artist. My father was a very good amateur carver, and none of that wore off on me or in their genes that they passed to me. When we put the test tube in the water, this should be 50 degrees Celsius. How do you do that? First of all, you put a couple boiling chips in there just in case to make sure it doesn't bump. But you heat it just long enough until you see a couple of bubbles at the bottom. And you shut off the heat, but leave it on the hot plate. And that gets this water to 50 degrees. You'll put the test tube in the water. After a certain period of time, different esters take different time. You will take the test tube and in a beaker with ice, you'll pour the test tube into the ice, and you'll take the beaker, swirl it a couple of times carefully, because there's sulfuric acid in there, and carefully smell it this way. Don't stick your nose in there. You should never do that with any chemical, especially with a beaker with sulfuric acid. So in part 1A, you're going to take 2 large test tubes. In each one, you'll place 1 milliliter of glacial acetic acid. Now, I don't know how it evolved. One day when I have time, I'll look it up on the internet. But pure acetic acid, 100%, is called glacial acetic. I don't know how they got the name other than it's super clear like a glacier in the Antarctic or the North Pole, who knows? But be careful. And I warn students, you do this in a hood because how many of you have ever smelled vinegar? It's got a strong smell to it. That's only 4%. You'll be using 100% acetic acid. Now, in one test tube, let's call this test tube A and test tube B. You'll have the glacial acetic acid, which is the structure for acetic acid. And then one of them, you'll add the isoamyl, which is a common name, and I also give you the UPAC name. You'll put the isoamyl alcohol, and then later on, you'll add the sulfuric acid. The other test tube, you'll put also 1 milliliter of glacial acetic acid, but you'll put into this one ethanol. And I think I had ethanol first. Doesn't matter which you call A and B. So there's your each one, and you'll make an A, one ester, a different ester in B. You'll put the test tubes in a beaker of warm water for 10 minutes. Then you'll take a small beaker, put some ice in there, and pour in one beaker, test tube A, and smell that beaker. In the other beaker, beaker B, you'll pour test tube B and smell it. And you'll identify what's the odor. Now, since we're not going to do this at home, if you were in the class, in the lab, you would smell, and I go walk around and help people, you would smell the one with ethanol and acetic acid, smells like nail polish remover. Now, the other one, the isoamyl alcohol and acetic acid, don't forget that table, you have to draw the structures for the esters form. It would smell sort of like a banana. Now, it's interesting when we do this face to face, I go around and tell students for that one with the isoamyl alcohol, if you can't identify it, call me over and I'll help you. And students, I don't know, it doesn't sort of, I'm not sure. And they say, does this smell like something yellow? Yellow? Like a fruit that's yellow? And all of a sudden, somebody will always say, oh, that smells like, I think it's Laffy Taffy banana or Taffy Laffy banana. And I say, now put it farther away from your nose and go like this. What does it smell like? And I say, a banana. Dr. White doesn't like bananas, but I still like that ester lab. And ooh, banana. I hate bananas. Yeah, yeah. You can have all my bananas. My mother used to love, the Sara Lee banana cake, and it's got that banana frosting on it. When we'd have it for dessert for dinner, here, give it to my sisters or my mother or father. You can have my piece. I don't want it. And I never did. But the reason students were having trouble identifying the smell of that ester that was a banana is when you smell it from the beaker, you're getting a large amount of ester up your nose, a large amount. When you smell it from a banana, you're just getting a little ester. And that concentration throws your brain off. I sort of know what it smells like, but by holding it farther away, you lower the concentration. Now, in part B, you'll use salicylic acid. You have to look up the structure of that and react it with methanol, and you'll make an ester. Same thing, put the carboxylic acid in the test tube, 5 milliliters of methanol, then in a hood, add dropwise slowly some sulfuric acid, carefully mix it. For this, you don't use the vibro mixer. Pretend this is a test tube, hold it, go 1, 2, 3, 4, don't tickle it, and you'll mix it. And you put it in that same warm water. This takes a little longer, 15 minutes. I usually tell people do part B and C first. And then you'll pour that into a small beaker with ice and you'll smell it. And if you were there in lab, you'd smell it. It smells minty or like mint lifesavers. And this is called oil of wintergreen, which is mint. Now, in part C, you'll take the glacial acetic acid. Remember, glacial means 100%. You'll add 1.5 milliliters of 1-octanol, the alcohol. You'll add a little sulfuric acid. Again, you're making an ester. You'll put it in the warm beaker. This one I tell people do first because it takes 20 minutes. And after 20 minutes, you'll pour it into the ice and beaker, small beaker with ice. Carefully smell it. And what do you smell? Well, it smells fruity. And if you really think about it, hold it a little farther away, it has a smell similar to an orange. And this is one of the esters that is in the, causes the smell and taste of oranges. We don't taste this because there's sulfuric acid in there. You'd be in the hospital or worse. And don't forget to draw the ester, just like in this table, draw the ester in there. All right, now this next part I have some fun with, and I know this industry. And if we were face to face in the lab, I had Dr. Daly buy me some, and that is I'd have a diaper. Diaper, yeah. And it was one of those super absorbent diapers. And I would talk about the following. And that's polysodium acrylate, also known as SAP, superabsorbent polymer. And this is a superabsorbent polymer that absorbs the moisture in urine in a diaper. And it also is used in feminine hygiene products to absorb the liquid mainly, which is water, during that time of the month. And this is very sophisticated chemistry. And I actually, the main company that had the patent for this for 20 years And when I went, it was about a year or two before they sold it. This was when they sold that industry, the rights or that industry, because it became they no longer had the patent rights. I forgot how many $1 billion they got for it. It's a huge industry. Well, in this lab, you'll be investigating sodium polyacrylate with water and hydrochloric acid, and also base. Let's take a look at sodium polyacrylate. It's a carboxylate anion. Oops. Of this structure where N is on the order of about 1 million. Now, carboxylate anions are bases. If you add an acid to it, like HCl, you'll form the carboxylate anion, or carboxylic acid. I was going backward. Now, this, is a acid, and if I add sodium hydroxide, I'll get back the carboxylate anion. And the question is, which is a better hydrogen bonding to water, tie up water, the carboxylate anion or the carboxylic acid? In this lab, what you'll do is first treat this with HCl till it's acidic, and you'll protonate it. And then you'll add sodium hydroxide solution till the pH is basic. And we're doing this in water, or with some water around the sodium hydroxide and the HCl are aqueous solutions. And again, acidic proton base. You'll get back the carboxylate anion. And the question is, which is a better hydrogen bonding? Because remember, this molecule, it's a polymer, it's a white powder, is used to absorb water in either urine for babies or blood for that time of the year, month for women. And what you'll do is weigh 1/10 of a gram of the sodium polyacrylate and place it in a 50 or 100 milliliter beaker. We have both in your drawer. Then if we were face to face, you'd add another beaker, you'd add the same thing. And to each beaker, you'd add 5 milliliters. DI stands for deionized water. And then you'd mix it and observe what you see. To the second beaker, you'd add slowly 1 molar HCl solution till the pH, which you measure with pH paper. If we're in the lab, I'd remind you how to use that till the pH is lower, 5 or lower. It's acidic. And like I said, pH can be measured with pH paper. And you observe what you see in that beaker. Next, that same beaker, you'd now add dropwise 1 molar sodium hydroxide solution of base until the pH is 8 or higher. It's basic. And you observe what's in that beaker. Now, in the first beaker, with distilled water and the sodium polyacrylate, it becomes a gel. How many of you have ever seen the product where you can put water in a dish and it gels up and you can put plants in there or candles on top? Well, it becomes a gel. Now, we don't do anything more to the first beaker, which is why there's a dashed line in those next two boxes. In beaker 2, guess what? The same thing happens. It becomes a gel. Now, when you add enough of hydrochloric acid solution to get it acidic, it's now liquid. And then that same beaker, when you now add base to it, sodium hydroxide, to make it basic, it becomes a gel again. And unfortunately, I don't have a, hold on 1 second. Maybe more than 1 second. Let's do something I've never done before. Well, this could be dangerous. All right. Everybody see that on your screen? What's the sodium polyacrylate? Puts the water, waits a few seconds. Oh my God, it's a gel. It hydrogen bonded that strongly. Oh, instant replay. And that stuff's neat to play with. Well, now you know I'm an organic chemist. Oh, let's see it one more time. Put the sodium poly, this you'd be using 1/10 of a gram and not this much water, but you can see the same thing happen. Is that amazing? And that's how a diaper works. And that's how feminine hygiene products that are super absorbent work. They absorb the water that quickly. Wow, that was neat. And you have your questions to answer. And with that was fun too. Fun to do. Oh, I like that YouTube video. And we've done it face to face. With that, I'm done for today. I'm done for the week, unless you want to stop by and say hello to me in my office hour tonight. You're always welcome to if you have any questions, or if you just want to stop by and say hello. And let me remind you again, next Wednesday will be test number 3. Hopefully you've been doing the practice problems. I'll help you on test number 3. And for those of you who are celebrating Ramadan, happy Ramadan. For those of you who are celebrating this Sunday Easter, happy Easter. For those of you who are celebrating starting night Passover, happy Passover. If you're not celebrating any of those, have a happy rest of the weekend. And with that, I'll say, Gang gesund. Goodbye.